With that, I think we'll just move on to the second session right away. And for that, I would like to introduce Chris Woodfield, who will be presenting Demystifying Clos fabrics. Chris is an automation architect at i3d.net and is coming to us today from Seattle, Washington. Some might say Chris is a long-time listener, first-time caller. I would say Chris is a coach and a mentor because I do get to work with him on the programming committee. And talking about the programming committee, you might have seen him on the stage many times moderating, but not necessarily doing a session or full-on session by himself. So we are happy. I think that was since 2016, right? That was the last one. So it's been a while, but we're happy, and it's a great pleasure to have Chris back with us today. Welcome, Chris.
Yes, it has been, in fact, almost 8 years since the last time I did an analog talk, which is kind of humbling, but okay. Okay, here we go. All right, hi, I'm Chris Woodfield. I've been again, longtime program committee member and extremely occasional speaker, so bear with me as I do this for the first time in a while. Starting off, who am I? It was suggested that I should Photoshop a beard on this portrait. Ran out of time to do that, but imagine a Alex's gray beard on my face, and you'll be looking at your traditional internet gray beard. I've been in networking for over 25 years, which is also a bit humbling to realize that I've been doing this job for over half my life now. Earlier in my career, I was a specialist on backbone and edge networking until one day about 10 years ago that I was put on loan to a data center network team who found themselves in need of some additional BGP know-how, which I was able to provide. And if you want more about that, go back to the talk I gave in 2016. Another thing, imposter syndrome is strong. I'm sure we all dealt with it sometime. I'm no exception. I'm not going to claim to have all the answers here. My hope is that you'll all be able to learn something from here. But let me know things that I haven't considered. I want to learn too, just as much as you do. So happy to take feedback and maybe iterate on another talk on this going down the line if this turns out to be a worthwhile tutorial. So please let me know what I'm missing. All right, so you want to build a Clos fabric. And I'll mention that, yes, the correct pronunciation is in fact Clos, not Clos. So for everyone in the room, if there's one thing you learn from this talk, it's Clos. How we started with the traditional L2 fat tree that many of you may remember from your CCNA exam prep. Where to start if you're building a new data center fabric, a new Clos fabric. What inputs should you be bringing into your design decisions, and what sort of outputs do you need, and how flexible do you need your outputs to be when you're building a new data center fabric. I'll go over a number of your design options and potential ways that you can evolve your design as you go, and then we'll get into the gory details of how you put it all together. This is going to be a very high-level talk. We're not going to see router configs in here. We're not going to see demos, but hopefully, what I can show you some interesting topologies and things to consider when you are embarking on your own data center designs and your Clos fabric designs. So, who here remembers the fat tree? If you are a networker of a certain age, you remember the 90s, 2000s CCNA and CCNP designs that all seem to assume that everything was going to be L2, VLANs, trunks, spanning tree, all of which did well for its time, but we've evolved beyond that. Why did these designs not scale? The biggest one that I can throw out is the fact that L2 doesn't L2 designs really don't give you many options as far as scaling your capacity. If you're looking at spanning tree protocol, you have a forwarding link, forwarding port, and a blocking port. You can do things like MST to put different VLANs on different forwarding ports, but in general, your load sharing in these designs is very coarse, and the failure domains also tend to be very coarsely ground. When a link failure would occur, a lot of traffic would move from one place to another, and you really couldn't scale beyond multiple devices. Most of the time, you really only had an active and a standby for any given layer in the network. For scaling bandwidth beyond a single port, your best options at the time was L2, was LACP. If we're talking about L2 still, LACP, ether channel trunking, that works great between two devices. There were solutions for running LACP across multi-chassis LACP. That is a thing, although I believe most of the implementations are proprietary, which is another can of worms. So over time, we started evolving networks and also the applications running the networks to not care so much about L2 adjacencies and start to run at L3, pure IP connectivity. And taking away assumptions of, do two hosts in different racks have to be on the same VLAN all the time? In many cases, yes, but those requirements tended to fall away with the evolution of newer application models. That said, rarely did the data center topology evolve with that. Newer topologies are a thing you can take into account once you're at a point where you can build a network with different application assumptions, but there was some evolution that had to happen first. To reiterate a little bit, this was pre-VXLAN. So you really didn't have L2 overlay networks. MPLS was at the time probably the best way to do any sort of overlay network, but that was something you more saw on a backbone than inside a data center. Spanning tree was your redundancy model, was your redundancy model for L2, which brings the issues of failover models and lack of fine-grained failover models, to put it that way. One thing you'll notice in this design is that you have links between the devices in each layer. Practically, that places some limits on how wide you may be able to scale an individual layer. You either have them together in a mesh or a ring topology, both of which are viable, but I wouldn't call them optimal. Last but not least, who here has not had a spanning tree meltdown in a data center? Everybody's seen this happen. You've got, if you have a stuck forwarding port, you have broadcast storms, you have, as we all know, Ethernet has no TTL, so you would have broadcast loops, and all sorts of interesting ways that an L2 based data center fabric could just melt down in totally new and interesting ways on a regular basis. Not that L3 data centers don't have their own catastrophic failure models, but they tend to have less of a hair trigger. I'll put it that way. So moving forward a little bit, or more correctly moving back. So the origins of what we've had this called by various names: the crossbar fabrics, and then eventually the Clos, the Clos fabric. The initial patent actually dates back to 1938. Bell Labs, of course, and the first implementation, and the reason that it got named after Charles Clos, a Bell Labs inventor who gets credit for the first first production design of a crossbar fabric, as he called it, a non-blocking switching network crossbar in 1952. Obviously, this was for voice calls, but all of the same concepts apply to what we call a Clos fabric today in IP networking. So some of the things I want to mention are relevant to both the original 1938 patent, 1950s design, and the data center fabrics we run today. The first one is that in a Clos fabric, your focus is on horizontal scaling of devices, not necessarily scaling the bandwidth between individual devices. Not that you can't scale the bandwidth up, but there's an emphasis on having a uniform amount of bandwidth between individual devices in a fabric. Not a hard rule, but a design principle that is worthwhile to adhere to. That switch to wider capacity takes advantage of ECMP, equal cost multipath, which we're all familiar with, which allows you to expand horizontally and send more traffic across more paths as opposed to fewer higher capacity paths. And with that, the individual bandwidth of an individual link no longer becomes your scaling factor. What does become your scaling factor is the aggregate bandwidth and port count of the devices that you're using in your fabric, and how wide can you go in that fabric, which with modern hardware you can actually go fairly wide. Sometimes it may not make sense to, but the capabilities are certainly there. One thing I'll call out that you will see in a Clos fabric that you will not see in earlier designs is that you should never have links between devices within a layer of a Clos fabric. If you have 4, 8 fabric switches, you will not see links between those devices. Any traffic and ideally you should never have traffic going across, say, your spine twice. You may have traffic going from one spine to another spine, but not back up to the same spine. If that's a traffic pattern, hopefully that's just because you've got some routing convergence that hasn't completely converged yet. And that should be rare. All right, so what happened that allowed, the Clos design is from the 50s. Why didn't we start with that? I think, there's a couple factors here. Calling these out in the order that they're not in my deck, I think the biggest one is, as I mentioned, there was dependence and requirements for L2 level connectivity that did not allow for the type of ECMP that we needed for a Clos fabric. MPLS, a 2.5 overlay was the first stab at that. Nowadays, we have VXLAN, Geneve, and other L3 encapsulation protocols which run over IP, run over your IP underlay, which does ECMP quite well. And I think that's one of the key enablers of L2 connectivity over a Clos fabric for a cluster of compute that requires it. I've worked on Clos fabrics and data center fabrics that don't need overlays at all, that do everything on L3. And if you can do that with yours, great, awesome. Don't worry about an overlay, but most people do still need overlays of some level. Speaking of ECMP and jumping back to bullet point 1, ECMP implementations in newer chipsets improved greatly over time. Going back 20 years, the most popular data center switch of the mid 2000s could only do ECMP up to 8 paths, and the output of the hash algorithm that mapped a packet to a path, the output of that algorithm was a 3-bit value, which is fine if you have 2 paths or 4 paths or 8 paths. Imagine in your head what that does if you only have, say, 7 links, or if you had 8 and 1 failed. You're now pushing literally twice the amount of traffic on one link than the rest. So that was definitely something that had to improve. And different vendors had better implementations. We're now in a place where I've seen 64, 128 wide ECMP capabilities on modern hardware, which I think is probably more than you need, but certainly means it does the lower numbers much better also. A lot of early implementations of layer 3 fabrics and large layer 3 fabrics started to run into scalability issues with IGP. If you have a large data center fabric, your ISIS link state database and your areas are going to get more and more complex, and you're going to have more. Your control planes are going to be You're going to see a lot more links bounce, more control plane STP runs, and you really need to be able to design that well from the outset to make that work, which you may or may not be able to do at the time. So we had RFC 7398. We have a number of newer implementations utilizing BGP as the IGP of a data center. Either eBGP or iBGP, which has returned a lot of the scalability of routing protocols in a data center design that I would not say that you can't run OSPF or ISIS as your routing protocol in a big data center, but the designs tend to be a bit more fragile. I'll say that. I'm sure someone out there will tell me I'm wrong about that, so happy to listen. So a few things that you want to ask yourself when you're starting to build a fabric. Is this going to be layer 3 only? Do you need an overlay? Are you going to be dual stack? I hope the answer is yes. And also, what are your scaling constraints? And I don't mean how many ports do you have. I mean things like how many cages. How many cages do you have? What's your square footage? How many racks is this going to scale to total? What are the bandwidth needs of each individual rack? What's going to be the link requirements of going to your host? I think we're well beyond 1 gig servers, but 10, 25, 100 gigs to each host. How many hosts are going to go in your rack? I'm seeing there seems to be a trend where we're seeing 2 RU hosts in racks as opposed to one rack unit for a number of reasons. Oversubscription requirements is something you definitely need to consider. As your individual bandwidth per host goes up, the ability of a host to saturate that link will go down, and you might find that your oversubscription requirements are going to be a lot more forgiving if you have, say, 100 gig ports to your host as opposed to 10. And finally, your failure tolerance. How many of these devices can you afford to lose at once? Something to think about when you're thinking about your failure tolerance is, what are your repair SLAs? If one of your fabric switches dies, starts malfunctioning, you have to take it off the network. How long is it going to take to get a replacement out there? How long is it going to take to get a field tech to replace it for you? If that's going to be measured in days instead of hours, build in a little bit more failure tolerance and a little more redundancy in, or lower your maximum bandwidth requirements to suit the redundancy that you have. I call these the golden rules. Do your design at the maximum scale that you'll know you need. Make sure that your port reservations take into account the largest fabric that you expect to have to build. And if that means you're wasting ports from the outset, then so be it. Split up your host facing versus fabric facing ports in a way that you will never find you never want to be in a position where you need more ports. Especially if you were dealing with fixed form factor switches as opposed to modular. That said, you never have to build it all at once. Build racks as they come, build your fabric. Don't build an 8 wide fabric day one. Build a 2 or 3 wide or 4, and then as capacity requirements make themselves apparent, then you can add capacity, and you can do that organically. And above all, make sure that you have a single source of truth for every bit of configuration you need. That doesn't mean install NetBox or build your own management system. And it doesn't necessarily need that everything has to be in one place. Just you don't want competing sources of truth. You don't want your configuration to not match. Your source of truth could be an Excel spreadsheet, or a text file. It doesn't really matter what it is. You just make sure you have one. We'll start extremely simple here. So we call this a 3-stage, and the reason it's called a 3-stage is because every packet flow is going to involve 3 devices maximum, leaf to spine to another leaf. Honestly, this may be all a lot of you need, depending on your scale you're going. If we're talking dozens of racks, not hundreds. Depending on the on your selection of switches, 2 could be all you need, maybe 3. But as your bandwidth requirements go up, you're going to want to make sure that you have the available ports and the available capacity to add spines as you go. So starting with the assumptions about hardware capabilities. I'm not talking about latest model hardware because 400 gig chips or chipsets are very expensive right now. But if that's your requirement, then feel free to scale up. Starting with, as I'm assuming, a 32 by 100 gig leaf switch, which gives you a decent number of uplinks, and then for downlinks, you can take your 100 gigs and split them out into 25 or 10 gig breakouts if you don't need 100 gigs to your host. And there are 2 rack unit 64 by 100 gig spines on the market that are all fixed form factor. 1 rack unit for your leaf, 2 rack units for your spine, and this is commodity hardware, but also the large vendors sell boxes with exactly the same capabilities, sometimes with their own chipsets and many times with the same merchant silicon. So if we start with our basic design here, I mean, this gets you 100 gigs per leaf at 50% redundancy. You lose 1 spine, you've got 100 gigs. So if you've got 10 gigs down to your 40 servers, that's still a 4-1 over subscription, which isn't great, but depending on your compute needs, maybe certainly all you need. If you need more capacity than that, the simple solution is just to add more spines. So even at 50% redundancy, this is 200 gigs per leaf. Again, if we're talking 10 by 40 hosts per rack, that's 2-1 oversubscription, which in most cases, is fine. But obviously, look at your own application profile to confirm that. And from there, we can continue to scale up. This is an example of an 8 spine, of a simple 8 spine fabric. Here's where things can get interesting, where it's a lot easier to support 25 gig or 100 gigs to your host, obviously with oversubscription assumptions built in. Something that happens as you add more devices and as you get beyond, say, 4 spine devices, is that your redundancy requirements may go down. So if you have 8 devices, the chances of you losing more than, say, 2 of them at a time is going to be substantially less than if you have 4, which statistically seems like the same, but practically tends to. And also back to how long does it take to get a device repaired or replaced when you have a failure. So just keep that in mind. As your device numbers goes up, you're having larger number of smaller elements. The chance of an individual element failure is going to go up. The chances of multiple concurrent failures is going to go down as you scale this, continue to scale this. Moving on to our next design pattern. I call this the super spine. Once you get beyond what you can do in a single cluster, you can connect clusters together of individual spine fabrics with, as we call a super spine here. I would say the 25% of you that need more than a simple fabric, this design should handle most of your needs. There's another design beyond this, but you're pretty much in hyperscaler territory if you get to that point. Now, the thing to keep in mind here is that your aggregate bandwidth between clusters is going to go up as as you add superspines, not necessarily as you add devices to individual clusters. So the recommendation here is to size each cluster of spines, spine 1, spine 2, with a number of racks sufficient that the individual bandwidth to each cluster is sufficient both inside the cluster and outside. But at this point, if we're talking about the same, everything's 100 gig uplinks, we've got 3.2 TB of capacity per cluster of inter-cluster capacity, because it's 8 by 4, built in a redundancy factor, and you've got several terabits per cluster here. And then you can continue to add clusters to that. And really, the limit here is, when in this particular design, your practical limit is the number of ports in your superspine devices. If you use fixed form factor, that's one thing. If you go to modular chassis here, you can get into four digits worth of racks with this design. That said, once you get to a certain size in your data center, think about your points of failure. This is one fabric. This one fabric could catastrophically fail. So if that's a concern, then think about maybe you don't need to go this big with a single fabric. Maybe you design 2 in the same room and interconnect those in a way that a failure in one can be isolated. So again, these are the general numbers for this particular design for a cluster. This is all assuming that all the links you see here are 100 gig ports. We haven't even talked about 400 gig yet. So some pretty impressive numbers with modern hardware that will hopefully handle most compute needs. Your mileage may vary. So if we go beyond that, then like I said, if you're Amazon or Meta or Microsoft, this is probably what you're familiar with. Where we take that one spine and split it up across multiple spines, and what you'll see here is that if we do a cluster that is 4 spines, the first spine of each cluster connects to one of those superspine sets or superspine planes. And what that does, the advantage of this design over the last one, is that it brings back your ECMP width down. So the last design, I think we saw an 8 wide superspine. I've seen them in 16, 32, which works well, but as your aggregate bandwidth goes up and the number of links you're spraying it across goes up, the chance of an individual link becoming congested goes up as well. So this tends to bring that ECMP width down in a way that helps prevent individual link congestion. So limits the uplinks, and this gets you a lot more devices. Now, many of these are going back to fixed form factor, but once you're and one thing at this point, there's no way to make sense of a design like this without top to bottom automation. This is going to have to be a design where you are automatically generating configurations for every devices and have automated management of those. Otherwise you're going to spend more time logging into dealing with individual configurations than dealing with your network as a whole or your network as a system. So moving on to that. Protocol choices. eBGP tends to be the most widely used data center design, data routing protocol for data centers nowadays. That's not a hard choice, and plenty of people still use OSPF or ISIS as a data center design. Keep in mind that if you're running EVPN, you will still need to be running BGP at least between your leaf switches, generally an IBGP model, if you're not using eBGP throughout. If you're familiar with 7398, use a few points there, is that that is designed where each element is its own ASN, and all of your links between elements, between layers, are eBGP based. One quirk of that is that you can duplicate an AS number across layers, so across individual devices in one cluster, across the devices in a single superspine, and the advantage to doing that is that you get loop detection for free. You will not have to worry about a BGP path that takes you from one device in a individual spine plane to another device in the same spine plane, because seeing that same AS in the path will prevent those from getting installed in your rib or fib. Be careful where you aggregate. I've seen many failure modes where aggregating networks between one layer to another has caused individuals problems downstream, where a spine might see an aggregate route across all four members of a cluster, but then it forwards the packet to one, and guess what? That one cluster device, or the one leaf, or that one spine doesn't have a link to that rack. That particular rack link is down. So the only way to resolve that is to loop it within that cluster to get it to the rack it needs to go, which is not optimal. So just be careful with aggregation decisions. eBGP in particular, people have concerns about the hello timers, the hello hold down timers in BGP, but eBGP is very responsive to link loss. If a port goes down, that session drops pretty much immediately, and prefix updates could propagate very quickly. So if that's a concern, you can also run BFD, which will get you a better failure response time. Final notes. Please run v6. Please run dual stack. Very few networks are going to be v4 only now or in the future. If they're v4 only now, they will probably not be. So, please consider a dual stack design. If you're running only overlay traffic as your production traffic load, you can run a v6 only underlay. Any piece of modern hardware will support this, in my experience. And if there are that don't, then maybe look at different vendors. Aggregate the links in your devices. So your loopback, your link nets, all of your link nets that's one place where it is safe to aggregate, and that gets you some fairly cheap route optimization, fewer prefixes. Something to keep in mind is that IPv4 host TCAM is something you'll find on most commodity hardware. So 32 exact match prefix matches pretty much are free. The same is not true for /128. So in the last design I did, I actually brought the loopback of the switch into the same aggregate as the link nets. That way there was 1/64 for everything hardware related to that switch, and I didn't have to have a 128 for every device loopback floating around. If you haven't heard of GShut, take a look at it. It is the BGP equivalent of ISIS or OSPF overload. Most network operating systems have this already built in, but if it doesn't, it's fairly cheap to implement in policy. Last bit, I know I'm running a little bit over. One of the biggest things that issues you'll run into when monitoring and operating this is just the fact that there are so many paths between two hosts. In this particular example, there are 128 possible paths between two individual racks, and one of those paths is dropping traffic, and that can kind of ruin your day. And that's kind of a necessary evil when you have to start scaling wider and wider. But your tooling, and the basic answer to that is make sure that the monitoring you uses, exercises traffic across a wide number of flows. Simple ping just is not going to do anymore. Ping mesh is probably the best tool I've seen for exercising all possible paths between 2 points in a wide fabric like this. I colored one of the lines in this diagram a different shade of red just to illustrate that, there is a bad path in here. Which one is it? I couldn't tell you, and you'll need tools to figure it out yourself. So please implement monitoring tooling and implement some automated troubleshooting steps. So I left off a summary slide, so I will end with thank you and open for questions if there's time. I've gone a bit over, I realize. Okay. That's the overtime that's because I started late, right? Okay.
Hey,
All right.
how
Hi.
you doing? Mao from Nokia. You mentioned about the ISIS or EVGP.
Mhm.
If you had a really big network data center and being people talking about the convergence problem of EVGP, talk about ISIS as maybe a good replacement. What do you think about that?
I don't see any issue with running. Like I said, I am not a protocol evangelist, but in general, what I've seen, at least the networks I've operated, is that IGPs like OSPF, ISIS probably scales better than OSPF somewhat. Yeah, same hard limits. But generally, what happens is that as your area domains widen, individual, you have to run STP every time a link in that area fails, which your control plane may or may not be able to handle. But try it out, run in a lab and see what is the cost of an individual link failure in both ISIS, OSPF, BGP, and decide what works better for your network. My personal experience is primarily with eBGP, and yes, there are convergence issues with eBGP, but I haven't seen ISIS or OSPF be significantly better in my experience. Other people's experience may be different from mine.
Okay, thank you. And just last question is, I'm seeing also people talking about segment routing for the data center. What is your opinion about that?
I'm sorry, could you repeat that, please?
Using segment routing for the data center instead to go with the EVPN and things like that. What is your opinion about that?
SR and EVPN are both viable solutions to similar issues. My personal experience is with EVPN, which is why I really didn't touch on segment routing in this talk. But happy to take that feedback.
Hey, Chris, Jason Bodie, Moody's. Fantastic talk. Music
Thanks.
to my ears with the current in-flight projects that are on my plate. I have a quick question about what you were, in your talk, you mentioned something about AS clustering, particularly at like the spine aggregation or something. There was a bit snippet in there. So I kind of wanted to see if you could elaborate on that a little bit. I think it was to help with looping, I believe, right? And then lastly, thank you for the G-Shut plug. I think everyone needs to be adopting that because that helps you immensely in draining traffic when something needs to be upgraded.
Yeah, I wasn't aware of G-Shut at first, and then after we actually built one of these, and I was like, oh, okay, that's an easy solution. Wow. So anyway, the loop prevention issue is that there's a number of times, especially when you have a network that is converging, where you may have a path that loops where for at least briefly, there is a path that goes through two devices in the same layer. So in the same spine, in the same super spine layer, in the same spine cluster. If those paths are suboptimal paths, and to be honest, should never be considered because you actually wind up with an ECMP explosion at the same time. And we've all seen how well Broadcom's chips handle that. So if you give that cluster the same, if you assign the same AS number to all the devices in a particular spine, then those paths will never make it. What?
Spine pairings, you mean?
Yeah.
Got it.
Those paths will never wind up in your rib to begin with because they'll be dropped at the second spine that hears it because it sees its own AS in the path.
Perfect. Thank you.
Mm-hmm.
Hey, Chris. Aaron Natasha Akamai. Great talk. I would love to see a future iteration with regards to how the border layer interacts with the data center fabric. So excited to see that possibly for next time.
Okay.
I had a question about ping mesh. Is this a RFC standard? Is it a GitHub project?
It's a GitHub project.
Okay, cool.
I believe that I forget the name of the company that publishes it, but there's open source versions. It's one of those freemium style, but I want to say it originally came from our friends in Redmond, but don't quote me on that.
Okay. Could you summarize like high level?
It's an agent model that more or less does UDP pings to as many other hosts in your network as you want. And the key to that is it it will do unique source destination tuples. So eventually, if you're testing flows between host A and host B, you will eventually get to test every path possible between those two devices, and then you can build as big a mesh as you want, and then proactively catch forwarding issues that might not be hard up, hard down. Maybe you've got a stuck entry in a one device's TCAM chip somewhere, and ping mesh will catch those far more quickly than other tools that I've seen.
Nice. And quickly, you mentioned BFD, I think, in one of your slides. Like, how do you see that exactly being proactive or positive or negative in these?
I see BFD as a way to catch a failure that may not be a hard link failure. So if you've got an eBGP between the devices, if a link goes down on both sides, the peers, an eBGP peer is going to drop right away. But if you're peering with loopbacks, for example, and depending on their IGP, your classic IBGP model, but you want that to fail quickly, without necessarily that adjacency loss being the direct cost of a link failure, BFD is going to be a way to get you a faster failover than waiting for eBGP itself to time out.
Sure. Thanks so much.
Okay, last two. Thanks.
Eric Miller from GigStream. We're a small service provider. I have a question about when you have your collection of spines and leafs, net AS set or collection of ASs, when you get to your border, are you finding that it's better to run an old school like confederation, remove private AS?
Generally, remove private AS works well.
Okay.
That's also going to be your aggregation point. So if you've got generally what's going to happen is one of your clusters can serve as your edge cluster. So if I go back to say, this design, imagine one of those clusters, instead of maybe having leaf switches hanging off of it, that's your border.
Okay.
That can be your border. And at that point, is generally where you most often see aggregation of those data center prefixes out to your backbone. You might be leaking some host IPs or some anycast as well. But generally the best thing I've seen is to just remove private AS at that point.
Okay.
At that
and
border.
then second, if I have time, is do you see the solution supporting full routing tables, like full internet default free zones?
Really depends on your hardware choices. Most data center switches, no. I'm.
Okay.
Alex is shaking his head, but yeah,
You weigh in.
honestly,
Yeah.
devices that can support a full rib are going to be way too expensive for a data center implementation.
Gotcha.
They exist, but
We can take this out into the hall.
okay. Last question.
Alex Latsko speaking for netbusters.com. Oh, come on, I've had the domain for 25 years. Can I use it somewhere? In your research, did you find any examples of high water or low water marks where the simplicity of an IGP is not worth the effort when dealing with an eBGP as IGP, considering the current scaling of OSPF and ISIS? You can run up to 32,000 in a zone. For practical purposes, you don't want to run over 1,000 or so switches in a zone, but for practical purposes, you don't want to go that big with a 2 or 3 layer closed network.
I've seen the tip, in my experience, the tipping point tends to be right around that number, high hundreds, low 1,000 racks total. And the big question is how are you, what are your area boundaries? Like if everything between super spine and all the individual spines in this diagram, if that's area 0, you better have some modern hardware that can handle that can handle the control plane overhead of dealing with the link failures you're going to see and how often you're going to have to be recalculating spanning tree.
I will.
You're going to disagree with me, aren't you?
Well, no, I'll note that I've put 1,000 devices into Area 0 on an EX3200 cluster.
Okay.
But I wouldn't do that in production. then a comment is based on border information. If you think back about 4 years ago, Igor did a presentation on exactly that. So suggest referencing back to Igor's prezo.
Okay. All right. Thank you.
Thank you.
Well, thank you all.